All right, here we are, friends, again. Look, we have two cameras again because we just can't hold it all on one. So, this is our final program of the summer, y'all. But we're going to still have other things on Facebook and Instagram and YouTube that you can watch and look and see all kinds of fun stuff. And we have Mr. Bond's Science Guys. And this is one of the coolest ones because he's going to do some really cool stuff. This is Haz-Matt. And so pretend like you all are here and go, yay!
Hello everybody, my name is Haz-Matt and I'm from Mr. Bond's Science Guys. Thank you all for having me so much. I'm so happy to be here. Today we're going to be kind of studying a history of energy and a history of work. So everybody put your hands up like this. Good. Okay, put them down. Up, a down, up. Okay, you can stop. Now, what you just did there, you just did work, right? And humans have been doing work for a long time, for many, many years, right? And how do we get that energy to do our work? Well, we eat food, right? That's how we get our energy to do work, but there are better ways to do it. You see, when we built the pyramids, we used human energy and maybe some animal energy, but we're only relying on what one being can do. So we're going to take a journey through history and find out some of the innovations we've made to make our lives easier, right? One of the first things we invented, obviously, was fire, right? If you can harness fire, I guess we didn't invent it, but we harnessed it, we can cook our food. And if you cook your food, it becomes easier to digest, right? You don't have to work so hard. Your life is a little easier because you burnt something. Great. You can stay up later at night, right? So I actually have the first experiment we're going to do today is a fireball. And we might have to go outside to do it because it could set off the smoke alarm here. So we need three things for fire to live, right? We need fuel, we need oxygen, plenty of it in the air around, and we need heat. So I'll create my heat with my flame that already exists. This is my fuel and the oxygen already exists. Now this is lycopodium powder. It's a fine powder that is pretty flammable. But if you just try to light it on fire by itself, nothing really much happens. It needs to be mixed with the oxygen in the air. And in fact, you might have seen a grain silo before. What grain silos hold is food, right? And sometimes some of those particles of food go up in the air and they mix with oxygen, and even the smallest spark can ignite the whole thing. So they have to be really careful. So we're gonna be really careful around here. We have our fire extinguishers over to the side here. We're being really safe, and I can always run and jump in the grass if I have to, right? Okay, so here we go. 3, 2, 1. Oops, I put out my fire. Let's try again. 3, 2. Whoa! That was a great one. Does everybody still have their eyebrows? You guys good? Okay, cool. Check your eyebrows. Make sure you're still good over there. Should we try it again?
Yes.
Yes? Okay, cool. We're outside. It should be safe. It's fine. But for you at home, I need you all to raise your hand, and you can raise your hands too. Everybody repeat after me. Say, I will never ever play with fire unless I'm with Haz-Matt. That's me.
That's me.
No, that's me. Not you. No, just, all right, just like, listen, just don't do this at home. It gets out of control faster than you realize. Let's try one more time. 3, 2, 1. Wow! Oh, cool. All right, so that's the first development that we did. Let's go inside and look at a few more. Cool, right? So fire we had mastered, and we had our human energy for a long time. We just had those two things. It wasn't until about the Industrial Revolution, just over 200 years ago, when we really started to harness our energy to do more work for us all the time. One of the first great inventions that we came up with was the steam engine, the locomotive, right? It used to be that we had to ride a horse to get across the country, but now we have this massive engine with these small little explosions happening that can get us across the country. And it takes advantage of something called the states of matter, something going from cooler to hotter, expanding and creating energy. You see, you can look at this and think of it as water. Every one of the yellow points is a molecule of water. And in its coldest state, we might call it ice, right? There's not a lot of energy to ice. As we change our phase of energy and go from ice into water, we gain more energy. And those molecules start to bounce around and move around. As it goes from water to a gas, though, lots more energy. Wham, it gets really big. It starts moving all around the room. The gas molecules are jumping around. The more heat you add. And of course, it works the same way going backwards. Higher energy, lower energy, lowest energy when it's cold, right? And so steam engines take advantage of that same idea, right? If you put a small piece of fuel in a contained space and then bottle it up, then it can explode and be a lot more energetic. So we're going to try that using scientist's best friend, dry ice. You might have seen it before, right? This is dry ice, and I'm just down to a little bit more of it, so I'm so glad we got to this. This is dry ice I have right here, and it's so cold that if I were to touch it without a glove, it would give me frostbite. Some people say it would burn me, but that's not quite right. It would give me frostbite. And what it's doing right now is it's taking water vapor out of the air and making real snow on the top. Just from the water in the room, I can make the world's smallest blizzard right at you. 3, 2, 1. Cool, right? So I made snow just from standing in a room with water, just by having something cold. Now what we're going to do is we're going to put some of our dry ice into a container. All right, so I'm going to break up my dry ice. I'm going to put it inside of my container. And when I heat it up, I'm going to add energy. I'm going to have that gas expanding. It's going from a solid all the way to a gas, by the way. So it's going from this to this really fast. And you can imagine what would happen if we covered it up. What happens if we put the top on? Explosion, right? Very good. Yeah, so I'm going to hold on to this. And I'm going to add some hot water inside. And that should, first of all, show us our gas, right? Going from a solid to a gas, turning into carbon dioxide gas through a special process. You might know what this is called. It starts with an S. It's not evaporation or melting or anything like that. It starts with an S. Anybody? Starts with an S, ends with an ublimation. Anybody? Okay, sublimation if you didn't know, right? Sublimating gas, it's expanding rapidly. Now let's put the top on. Now wait a minute, if it's not going off, should I look at it and say, why isn't it going off? Don't do that. You don't want to point it at your face. That's rule number 1. So I'm going to hold it, top on. Let's see if I can count down. 3, 2, 1. That was pretty cool. Right, so similar technology to how trains work. They have gas expanding, and then that creates motion, creates work, and we can travel across the country. Let's see if it works again. Now, this water is getting colder because the ice has been in there for longer, so it should take a little bit longer. Oh, nice. And one more. Let's see if I can get a good count. I'm going to guess 10 seconds. 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. -1. -2. So you notice it takes longer each time. As the water gets colder, do we have more or less energy? Right, less energy. That's correct. All right, so that's pretty cool. But what if we put fire in a container and then lit it and made that explosion? Would it be bigger, smaller? Should we try it? All right, let's give it a go. This is also something that was really important in the Industrial Revolution. We found ways to make burning things create more energy by compressing them. So, oh, put the lid on. Oops. So I'm going to put some of my fuel, and I'm going to create an electrical charge, and we should be able to get a nice reaction, and it'll probably be even more explosive than before. Because now we're creating a chemical reaction where the fire is burning. Let's try it out. 3, 2, 1. Ooh. Now that's how a car engine works. Little tiny explosions that make it go faster and faster. So all of these developments are helping us do our work better and better all the time. So, great. So for this next experiment, we have my favorite scientist of all time. You might have heard of him. His name is Tesla. And you're probably thinking, the car, the electric vehicle invented by Elon Musk. No, actually Elon Musk named his car after the great Nikola Tesla. He was a man who mastered electrical energy. And in fact, he went to my hometown of Colorado Springs and he created wireless energy over 100 years ago. Wireless energy. Before we wired everything for the last 100 years, he was doing things wirelessly. And what he did is he put these light bulbs in the ground and he sent out these waves of energy and they all lit up. And we're going to do that right now. We're going to turn off the lights in this room. And I've got my Tesla coil here on the table. And once I turn it on, it's going to create an electrical magnetic field all around it. All right, so I'm going to turn that on. And what you'll notice is when I bring my light bulb closer to the coil, wow, there it is, wow. I don't even have to touch it to the coil, everybody, and it's still lighting up. This is the genius of Tesla. He says we don't need wires. We can create electrical energy just by having the electrical magnetic field in the air. One of my favorite experiments to do. And it's almost like I'm on Star Wars or something. Cool. Now, we can bring the lights on for a minute, and I'll show you my next Tesla invention. It's actually a similar idea. It's called a Tesla coil, but it's a handheld version. Old Tesla invented this and sold this to a man named Odin, so they call it an Odin coil, but it's still Tesla's invention. And now I'm going to give my light bulb to the librarian. And you're going to hold the light bulb, but just make sure you don't touch the metal part accidentally to your stomach or stick it up your nose or anything weird like that. We don't want to,
No.
So,
I won't do that.
This Tesla coil, the electricity comes out of the tip. Rule number 1, don't touch the tip. It's a good start, right? Rule number 2, don't touch your friends with the tip. But of course, the most important rule, don't touch me with the tip. All right, cool. Yeah, you got it.
And don't touch the librarian with the tip.
No, oh yes, the most important rule, really. So as I turn my power source on, I'm creating a charge. And that charge is looking for the opposite charge. You might have heard a little bit about electromagnetism. We'll have one charge here, and it'll connect to the opposite charge somewhere else, and then you get a bolt of lightning. And that's what we're looking to do here. Maybe if we just turned off half the lights, we could see both of us and still see the light bulb. That would be a good way to go. So I've got my power on. It's already lighting up the light bulb, but when I touch it down and you see the lightning, it's alive!
Oh my goodness.
That's pretty cool. Now, if you notice out there in internet land, where does that light stop? You can't quite see it on this camera, but that light is stopping at your hand, isn't it?
Oh, it is.
Now that's because the electricity is always trying to find its path towards the ground. And believe it or not, it's choosing to go through your hand and down into the ground through your feet. But you don't feel it because you're already a part of the circuit. Watch, now move your hand up here and let go of that other one. See? It's really clear in the room, but harder to see on the camera. It is stopping at her hand to some degree, right? Did that hurt you?
No.
Okay, good. So we'll have to try harder. No, I'm just kidding. All right. So Tesla invented, you can turn them on. Yeah, that's fine. Tesla invented this nice coil, but he also invented the electricity that we have in our houses and our schools. It's called AC current, and it was a little bit safer than the DC current that Thomas Edison was using at the time. So we're thankful for that very much. Mr. Nikolai Tesla, also he invented lasers and all sorts of cool things. Check him out if you don't know about him. Now you may or may not know, magnetism is closely related to electricity. In fact, a lot of people say they're two sides of the same coin. They're basically the same thing. And it turns out magnetism can do some pretty cool things in relation to electricity. So first of all, what do magnets attract to? Well, metal, sure, we got that. But there are 3 metals that they attract to on this earth at this temperature, at this pressure. One is iron. This is a pretty strong magnet, actually. It's quite hard to get off. Another one is steel, but that's still iron, so we'll count that as 1 still. The other 2, the first one starts with an N and ends with an nickel. It's a 5-cent coin, nickel. And the last one is cobalt. So iron, nickel, and cobalt. This is an iron pipe, but I did not say copper. Remember that. Copper is not a magnetic metal, right? But it turns out when you have magnetism close to something that conducts electricity, you can actually create magnetism where there wasn't any before. So if I drop this magnet through my pipe, my guess is that gravity is going to take about 1 second to get down to the bottom, right? I mean, that's all it takes to drop from here to here, right? So what if What if we dropped it through the pipe? How long would it take? 1 second. Let's try and count it out. Ready? On your marks, get set, go. 1, 2, 3, 4. Wait a minute, something weird happened there. I expected it to take a second. Copper is not magnetic, and yet 1, 2, 3, 4 seconds to drop through the copper pipe. This is a peculiar thing happening here, but it's very important when it comes to science, technology. All of our hydroelectric power, all of our wind power is created from this principle. It's called Lenz's law. Magnets, you might know, have a positive and a negative. When you move a positive and a negative, opposite charges, down through a conductor, you make a magnet where there was no magnet before. So I've created a magnetic field. And if it wasn't for gravity, that magnet would stay in there forever. And that's really cool. And so if you go the opposite way, you can have magnets moving around copper and it makes electricity. So cool. Now, this is also a conductor. This is tin foil. It's pretty light. It doesn't fall to the ground immediately. But when I put my electromagnetic wand underneath it, I can actually make it sort of turn into a magnet. And every part pushes away from every other part, like two negative magnets when you push them together. Check it out. I can make this float using only static electricity. Pretty cool. And as long as it doesn't get close to anything with the opposite charge, it'll never fall down or hit you in the... Oh, it attracted to me because I'm the opposite charge because I'm on the ground, right? Of course. So like charges, repelling, pushing away, even from my fly stick, as long as it doesn't get close to anything on the ground, it'll never hit you in the... I'm too close to it because I'm the opposite charge, right? The electricity is grounding. You get the idea. Pretty cool. Now, believe it or not, this is the wave of the future for our train travel. Trains of the future are going to run on electromagnetism, repelling energy so there's no friction where the train touches the ground. So it just can go really, really fast. Check it out. Okay, great. Now, for our last experiment of the day, we've seen how physical things can create energy through phase changes. But it turns out chemical reactions can also create energy to help us with our work. What I have here is ammonium dichromate. And ammonium dichromate, once you burn it, turns into a totally different thing. It turns into this wonderful green ash that you'll see, but it also turns into water vapor and nitrogen. Now, I would never burn something without knowing what I was burning and what I was breathing in after I burned it. And it turns out this is totally safe. But at the same time, since I am working with an orange chemical here that I don't want to touch, I'm going to use my safety glasses, and I'm going to make sure any hand that gets close to it, I'm going to use my safety glove as well. So, this is basically going to create sort of a volcano. You might have heard of the biggest explosion in the world called Krakatoa. It basically blew up the whole island, and that's what we're going to do here today. We're going to blow up the whole library. No, I'm just kidding. All right, what we're going to do is we're going to start this light on fire. We might bring the lights halfway down for this one. I'll start it. It takes a little bit of time to get it going, but once it starts, we'll just bring down one of these lights so you can really see how pretty this is. Now this stuff takes a minute to light, but once it lights, it'll go ahead and finish the entire reaction all by itself. Oh, there we go. There it goes. Now we're creating our little mini volcano, and all of the ash is flying up towards you in the camera world. And above that, it's creating a lot of heat. It's creating water vapor, and like I said, nitrogen, which of course we all breathe in all the time, so no worries there. Let's turn off the lights a little bit. Ooh, wow, look at that thing glow. That is so pretty. Cool, right? I really enjoyed hanging out with you guys today. If you want to check us out online, it's really easy to find us. We're in a couple different places. We have makesciencefun.com. We have MrBondScienceGuy.com, and we also have ScienceGuysOfBaltimore.com. We have a new branch, so that's pretty cool. Check us out on Instagram. Also, we are doing live summer camps all summer. So if you love science as much as I love science, come and join us on Zoom. We'll do Zoom sessions, about 20 kids, and we actually send science kits to your house. So we hope to see you there, guys. Take care.